Section 310 is about something called implicit differentiation. And so a lot of times you see this where you have equations in both x's and y's. And you can assume y is a function of x. And then using that you can solve for the derivative. So we're going to say, for our first example, we're going to consider x squared plus y squared equals 1. And then we want to find the slope of the tangent line on the graph at the point P equals 3/4, 4/5. Sorry, 3/5, 4/5. So here's how implicit differentiation works. We start with our equation. Our goal is to get dy dx. So we assume if y is a function of x, which means when you have y's to powers, or if you have a function evaluated at y, the chain rule will apply. So we're going to take this equation, we're going to apply d dx to both sides. D dx of x squared is 2x, that's easy. D dx of y squared, this is where we use the chain rule. Y is a function of x, so we get 2y, then times the derivative of y with respect to x, and this is what we'll eventually solve for. That equals d dx of 1, which is 0. So we'll scoot the 2x that doesn't have the dy dx on it across. We will divide the 2y across now. And then we'll get dy dx equals negative x over y. So here's the equation for our derivative. Now we just have to evaluate that derivative. We have to evaluate it at the point we're curious about. So you may note this rule is a little weird because our derivative depends on both x and y, whereas everything we've been doing up to here, it's just dependent on x's. So when you deal with implicit differentiation, that's kind of a weird thing that ends up happening. So we're going to take the x value of our point, we're going to replace the x with it, take the y value of our point, plug it in for y. We'll do keep change flip. And we'll get this is negative 3/4. Okay, so we're going to do a couple more examples on a few other equations. Just kind of get some more practice with it. So for this one, we got y to the 4th plus xy equals x cubed minus x plus 2. And we want to find dy dx. So we'll start out by taking dy dx of both sides of the equation, or sorry, d dx of both sides of the equation. We keep in mind we assume y is a function of x, so the chain rule applies to y's with powers. Otherwise, if it's just y itself, we'll write it as dy dx. Okay, so d dx of y to the 4th, that will be 4y cubed dy dx. When we want to do d dx of xy, the product rule applies. We leave x alone, take the derivative of y, which we don't know the derivative of y, so we write it as dy dx. Plus, now take the derivative of x leave the y alone. That equals d dx of x cubed is 3x squared. d dx of negative x is negative 1. d dx of 2 is nothing. Okay, this 1 times y has no d dx attached to it, so I'm going to multiply it, subtract it across. Just trying to gather all my terms that have dy dx's on one side, and everybody without a dy dx goes to the other side. Now, on this side, I'll factor out the dy dx. And then we'll divide everything across by this parentheses stuff. And that'll get us our dy dx. And then we're done. Again, a little weird because our answer does depend on both x's and y's. But once you get used to it, it's not too bad. Just got to remember when you do ddx, or ddx of like y to powers, like y to the fourth, the chain rule applies, so it kicks out of dy dx. That's usually, people forget that, and that's usually where these problems go wrong. So we got 2 more examples to do. So we want to find the slope of the tangent line at the point 1, 1. On graph. E to the x minus y equals 2x squared minus y squared. So we're going to start out doing d dx of both sides. And since this is an equation in both x's and y's, that's the tip-off that I need to do this d dx of both sides of my equation. Since my equation has both x's and y's in it, get the lights to kick back on. That indicates that I need to do I need to apply d dx and try to do it implicitly. Chain rule applies here. E is the outer function, so we get derivative of e is itself, leave the inner part alone. Then we multiply this by the derivative of the inner part. Derivative of x is 1, minus derivative of y with respect to x is dy dx. This equals d dx of 2x squared will just be 4x. 2 comes down, hits the 2 that's already there. Minus, now we want d dx of y squared, the chain rule applies. We get 2y dy dx. Okay, I need to get the dy dx's together, so I need to distribute this e to the terms here so I can get them broken up so I can shuffle them back and forth across the equal sign. Okay, so we got it here. Now I need to move all the dy dx terms. I'm going to bring them over here to the left. Anybody that doesn't have a dy dx, I'm pushing back over to the right hand side. Now I need to factor out the dy dx on the left hand side. I divide through by all this parentheses stuff that's multiplied to dy dx. That gets me dy dx solve for. So now that I got my equation, I can evaluate it at the point 1, 1. I replace x with 1, and I replace y's with 1 as well. See, this equals e to the 0 is 1, so this is 4 minus 1 over 2 minus 1. That is 3 over 1, which is 3. So the slope of my tangent line, or slope of the line tangent to the graph at the point 1, 1, happens to be 3 in this example. Okay. Now, this last problem here in the section is going to be something that you can use to speed up the problem sometimes. It really only works if you're only interested in the point. If you need the equation as well as the point, don't use this method. So here we want to find dy dt evaluated at the point P equals 0, 5 pi over 2. For we have y cosine of y plus t squared equals t cubed. So we're going to start out taking ddt of both sides. Oops, ddt of both sides. And product rule is going to apply on this first part because we have a y multiplied by all this stuff. So we're going to leave the y part alone. We'll take ddt of this. That'll be derivative of cosine is negative sine. Leave the inside stuff alone. And then by the chain rule, we multiply it by the derivative of the inside stuff. So now we get, that's the y left alone, derivative of this part. Now we get plus, we take the derivative of y with respect to t, leave the cosine part alone. That all equals ddt of t cubed, which is 3t squared. So now, if you can see, if we tried to solve this, things are going to get bad. Since we don't need the actual equation, we just need it evaluated at a point. So we don't need the actual equation. The problem only wants to know about information about the point 0, 5 pi over 2. We can plug that in now. So we can plug that in now and solve, and that'll be easier. If the problem asks you for the actual equation, or you have multiple points, don't do this because it's going to take a lot more time. But if you're only interested in like one equation evaluated at a point, we can plug in here, and then since we'll have numbers replacing the symbols, some of that stuff will simplify down, and then we can solve out the remaining stuff. So zeros replace t's, 5 pi's over 2 replace y's. So we're going to just go through. dy dt's stay dy dt's. Okay, so let's copy this all out. So we get 5 pi over 2 for that initial y times negative sine of 5 pi over 2 plus nothing is 5 pi over 2. All that times dy dt is still there. Plus 1 plus 0, so plus 1, plus dy dt cosine of 5 pi over 2 plus nothing equals nothing. So that simplified a little bit. 5 pi over 2 is coterminal with pi over 2. So sine of 5 pi over 2 is going to be 1. Cosine of 5 pi over 2 will be 0. So that simplifies stuff more. We get 5 pi over 2 times the negative 1 times the dy dt plus 1 plus dy dt times 0 is nothing, so that all equals 0. Okay, so again, if you need the equation, if you needed the equation at this point, you needed to go back to the original statement before we plugged in and solve from there. Since this particular problem, we were only curious about what was going on at this point right here. That allowed us to plug in and simplify rather than taking this whole mess and trying to get the dy dt isolated. We plugged in the numbers and a lot of stuff is cleaning up and our equations becoming a lot easier to deal with. So we get that. I'm going to slide this term across the equal sign. So it comes over as positive. And then I want to get rid of this, so I'll multiply it by the fraction flipped. So cancels, cancels, we get dy dt, here cancels, cancels, negative still around. So we get negative 1 is the slope of the tangent line to that graph at that particular point. Again, we could, if we needed to do a second point, we'd have to go back up to here and plug in the other point and resolve. If they wanted the equation up in this step, we needed to distribute everything out and then get all the dy dt stuff on one side and everybody without a dy dt on the other, and then get the dy dt isolated. But that'll do it for this.